Good afternoon, everyone, and a happy World Quantum Day to everybody. I'm really excited that we have World Quantum Day because it was really long overdue. Yeah, and I hope that it will become a wonderful tradition that will be with us forever. Yeah, so that is very, very nice. And in particular, I'm very grateful to the representatives of the other African countries that you see on the panel above me, probably, if you have the same Zoom settings. Yeah, for joining us, because that also gave us a very nice opportunity to network and promote quantum whatever in the whole continent. Yeah, so thank you very much to the organizers of the World Quantum Day for setting up this fantastic event. Yeah, so and it is my real big pleasure to introduce to you our today's speaker, who is Professor Yasser Omar from the University of Lisbon. And the big pleasure comes from the fact that he's the main promoter of the World Quantum Day. Yeah, and I assume that in his talk he will mention maybe briefly the history of World Quantum Day and the intention behind the special day. Yep. Yasser, just a very brief introduction. Studied physics at the University of Lisbon, but did his PhD, if I remember correctly, in Oxford, and is now associate professor at the University of Lisbon, where he set up also an institute for quantum technology and quantum information, or a group, and has been promoting quantum information and quantum computing and related topics, not only in Portugal, but across Europe, in many European initiatives, and also worldwide, yeah, with the establishment of the World Quantum Day. So we are really very happy to be able to have him with us this afternoon. So Yasser, people are here to listen to you, not to listen to me. If you would like to share your screen and start your presentation, you're most than welcome. And yeah, and maybe just one word to the panelists that I didn't introduce. Maybe we can do that after Yasser's talk. So maybe when we finish the webinar, don't disappear immediately, and it's a nice opportunity maybe to chat 5 minutes. Yeah. So thank you very much, Yasser. It's your show.
Oh, thank you very much, Francesco, for your very kind introduction and for the invitation and for setting this up. And also thanks to all the colleagues participating here in the panel, representing a bunch of African countries, and also to the participants. So I'm going, can you see my screen?
Yes, we can see.
Okay. Yeah. So I want to tell you about the work we're doing on exploring the potential for quantum computation for addressing the tracking of particles in accelerators. But first, as so let me just adjust my window a bit. As Francesco mentioned, let me tell you about the World Quantum Day initiative and wish you a happy World Quantum Day. So this is an initiative from quantum scientists in more than 65 countries, and thanks to Francesco, we could gather a bunch of colleagues from countries in the southern part of Africa. So thank you very much. So as you can see, we're getting pretty comprehensive coverage, and I hope we'll cover more countries in the future. And if you want to know more about this initiative, you can check the website or the Twitter feed. But essentially, the idea is to promote the public understanding of quantum science and technology. And by this way, we can also network with other scientists and help develop this domain even better. So I'm very happy with the strong involvement of Africa so far, which I hope will grow. And I also want to thank Francesco for organizing this event today so that we can include it in the World Quantum Day celebrations. And in particular, this is the event representing Africa. And so Francesco kindly invited the other colleagues from our World Quantum Network in Africa to be present. So thank you very much to all. And so we actually have events in Africa, in Asia, in Europe, North America, and South America. This was much beyond what we expected. So we thought that this year we would just have one minor launch just to declare the World Quantum Day and start the countdown for a proper celebration in a year's time in 2022 at the global scale. But in fact, the enthusiasm and the initiatives were very surprising and exceeding our expectations. So this is very, very nice. And also, I would like to say that the idea of the World Quantum Day is that it's a bottom-up initiative, so that anyone in the future, anywhere in the world, can come up with their own event or exhibition or debate or lab tour or whatever. And so we had agreed to have at least one talk for the launch, and this will be a talk today at 5 p.m. Central European Time by Alain Aspect, one of the pioneers of the recent developments of quantum physics, single photonics, etc. So this was initially the official launch event, but there's many other events happening, including this today, launching things in Africa. So I'm very happy that we have many launch events. And so please check the website for more information about that. Okay, so going back to tracking. So why particle tracking? How come a bunch of quantum information scientists, quantum computer scientists got interested in this problem in high energy physics? So first, let me tell you that this work is developed in the context of a European project called CUANTUM, Quantum Computing Solutions for High Energy Physics, involving the group of Andris Ambainis in Latvia, the group of Simone Montangero for the quantum simulation part in Padova, and my group in Lisbon, and also CERN as a partner. And this project is funded by a European research program called Quantera. And so we've been discussing this idea of exploring the potential of quantum computation for this type of problems in high energy physics data processing. And so the work I'm presenting today was born in the context of this project, where we are actually working on other fronts with other results, but let me tell you about our main results so far. And so the people involved in this work, I call them the quantum tracking team. On the Lisbon side, we have Akshat Kumar, Gonçalo Quinta, João Seixas, Pedram Bargassa, Sagar Pratapsi, and Duarte Magano. And on the Riga side in Latvia, we have Alexander Rivos, Andris Ambainis, Andris Locans, Adam Gloss, Maxims Dimitrievs, and Martin Kalish. So this was quite a nice collaboration, building on the expertise of the colleagues from quantum and classical computer science, colleagues in high energy physics, and colleagues in quantum information and quantum algorithmics like myself. And so to go to the problem of tracking. So as you know, the way we try to understand nature at its most fundamental level is to collide particles in particle accelerators like the Large Hadron Collider at CERN in Europe. This is a proton-proton collider, which is represented here in white, gray. And in fact, there are plans to expand such experiments to very large scales. So currently the LHC has a 27-kilometer radius. There's the idea of an upgrade to this program for a higher luminosity, so more particles, higher energies. So this is called the High-Luminosity LHC for the next 5-6 years. And there's even more speculative plans about a future circular collider with a much larger, I said radius, but I made a mistake, sorry. Much larger collider, as you can see here in this picture. But so the idea is that the energy and the number of particles will be increasing. And so how then do we then detect these particles and the results of these collisions? So what happens is the particles, in this case at LHC, the protons come in colliding beams, and so and when they collide, we call this an event, and so a multitude of other particles result from each of these collisions, and each particle resulting as a trajectory. And how do we detect this? We have detectors. So here I have an illustration of one of the LHC detectors, the compact muon solenoid, the CMS detector. And these detectors are different layers of sensors, and when these resulting particles cross these sensors, they deposit a bit of energy. They are detected in each of these sensors, and so we know that one particle passed here. We call this a hit, and then there and there. This is a discrete set of layers. So we have a set of discrete points in space, and we literally have to connect the dots and find out which correspond to actual trajectories from these resulting particles. And so why do we do these experiments? Why do we study these collisions? Well, there are still important things to understand in particle physics. We want to unveil the production of the mechanism behind the creation of hadronic particles. There's something in the chat. Let me check if it's something related to my talk. Okay, no. So of course, we may want better precision for the standard model of particle physics, and also very exciting, the potential to discover new particles associated to physics beyond the standard model. And these are rare events that we're trying to find. And so how do these collisions happen? So at CERN, there are bunches of 10 to the 11 protons colliding every 25 nanoseconds. Okay, so here I have bunches, so they go in bunches separated in time by 25 nanoseconds, and they are colliding. And so this represents a luminosity, meaning particles colliding of 10 to the 34 per centimeter square per second. And this corresponds to 20 events in elastic collisions per crossing. And so we have about 600 million events per second. So you see there's a lot of collisions happening, a lot of particles being produced. So there's actually in the LHC beam 2800 bunches, those that are separated by 25 nanoseconds. These detectors have a very large magnetic field and considered uniform, and so the trajectories will actually be helicoids. And so every 25 seconds, what happens is that this detector is sort of taking a picture of all the hits that happen in that instant. So we have a set of three-dimensional points of coordinates in 3 dimensions for all these hits in the detector. And so this represents just the global picture. This represents 40 million pictures per second. And this is too much data to be handled. It's impossible to process so much data. And so in the end, most of this data is discarded, and only about 1,000 pictures per second are recorded. This still represents, given the number of particles and hits in the detectors, this still represents 100 terabytes of data per second. So you see, this is one of the biggest of big data sets that we have. And so here's a photo of the CMS detector to give you a view of this impressive machinery that is involved in all this detection. And also here there's a diagram, and there's a person represented here in the bottom, and to give you a scale of this experiment. And as you can see, there's a bunch of concentric cylindrical layers, as well as end caps, meaning vertical detectors that you can see here. And so there's different types of detectors for different stages of the of the process, and also of the particles. And we'll be and so you see the beams, the colliding beams, they will meet here inside this detector. And so here the particles are produced, and so we want to find their trajectories. And so we'll be particularly interested in this light blue detector, which is key for establishing the trajectories of the particles. And this is it. This is just to tell you what tracking is about. We want to identify what particles were created in this collision by looking at their trajectories. And once we have their trajectories combined with other information from other detectors, then we can identify what was that particle, what's its nature, and its features. And so this is key to, you know, make sense of this experiment. So as I said, we'll be looking essentially to these silicon trackers here in the core of the detector. And let me zoom in to these silicon detectors, and as you can see, there's a layer of detectors here in these cylinders, red cylinders and blue cylinders, and there's also these end caps, these vertical sensors. And so each time a particle crosses one of these layers, one of these detectors, this is detected, this is sensed, and so we call a hit. So we have a point in 3D space with 3 coordinates, and we want to make sense of all these points. Okay, so this is a longitudinal cut of this detector, just to emphasize that here we have the cylindrical layers, here we have the end cap layers, and we have at the core these so-called pixel layers, which will be seeds for the Kalman filtering process that I will describe a bit ahead. Okay, so what's the tracking problem? So now imagine this transversal cut just of the cylindrical detectors. I have these different layers and I have hits, I have dots. And now I want to connect the dots, quite literally, right? So for example, if I look at this set of dots here, I hope you can see my mouse, it's pretty clear that this would be a trajectory, right? So there's not much ambiguity here. But if I now look at this set of points here, it's not really clear which trajectories are which, right? There's quite a different number of ways I could connect these dots, and this would yield different trajectories which would have a different meaning. And how do I know that I'm connecting the dots correctly? This is the tracking problem. How do I reconstruct the trajectories correctly? Okay, and so this is a very challenging computational problem. At LHC, we can have up to 78 collision points. Meaning these are each time there is a bunch crossing, and so these are the up to how many particles we can have, or vertices emerging, source of new particles, and then each of these vertices may be a source of 20 or so particles. So we have this many collision points, each of them generating 24 particles or so, and each of these particles will cross this large number of layers, depositing energy and being detected. So you see, we have many points to connect. This is very complex. And with the upgrade, the ongoing upgrade to LHC, to the so-called high-luminosity LHC, the pileup will be increased by a factor of 3, so making this even a more challenging computational problem. And so here's an estimate on the CPU seconds necessary for this, and you see that this has the expectation is that this will grow exponentially very soon. So here's 2021, and once the high luminosity LHC is up and running and collecting data, this will become an extremely challenging problem to address. Okay, immense amount of data will have to be discarded. Already today, I tell you, there's 40 million pictures, you only keep about 1,000. Still, that's 100 terabytes per second. Here, the number of pictures, the number of data points will be even more large, very intractable, and so you have to dispose of most of the data. And so the more data you discard, the more you reduce the chances of observing rare events that could mean new physics, etc. So this is really compromising seriously the success of such experiments. So how hard is particle tracking actually? Because I've been telling you this is a very hard problem. I've showed you some numbers, there's some predictions for CPU time, but technically, how hard is particle tracking, right? And now one of the originalities of our work is we really want to look at this from the computational complexity perspective. And of course, I understand that for particle physics experimentalists, this is maybe not so immediately relevant because they work with real finite numbers. They don't care about asymptotic scaling of an algorithm. But I'll show you soon why this is interesting, or at least that's our expectation. So let me set here the context. There's essentially two classes of methods to address the tracking problem. And so there's the so-called global methods, which are based on pattern recognition and machine learning, and these are essentially based on heuristics, and they are essentially clustering algorithms. And then there's a bottom-up approach, which I will describe next, which are local methods to reconstruct tracks one by one. And this is what we'll be studying here. So in particular, we'll be looking at, to the best of our knowledge, the state-of-the-art of this approach. And this is the combinatorial track finder algorithm developed by the CMS collaboration in 2014. And I want to acknowledge Felice Pantaleo, who was a driver in the development of this classical work, for very useful discussions with our team, where we learn a lot how this works. And I want to reproduce this to you here, because we decided to do a full computational complexity analysis on this algorithm. Okay, so this combinatorial track finder algorithm, this is what is currently used at CERN or similar, and is composed of 5 stages. So this is entirely classical, okay? So the first stage is the seed generation. So you need to find triples or sets of points which you consider would be the beginning of the trajectory you want to reconstruct. Okay, so you need to decide which initial points you will consider as the seed of a track. So this is already a computational challenge in itself. Then there is a track finding, right? So now I decide, okay, from this triplet of initial hits, I will try to find the 4th and the 5th and the etc. And reconstruct the trajectory point by point. So we will propagate the tracks layer by layer with something called the combinatorial Kalman filter. And we will stop only when the outermost layers are reached. So this we having candidate tracks for a solution of our problem. And then we want to do something called track. I mean, I say we, but this has been done by these colleagues from the CMS collaboration. Here we are just analyzing their classical algorithm. So then what is done is the so-called stage of track cleaning. So there might be some ambiguity and duplicity in tracks, more than one track for the same particle, and so this needs to be addressed. So we have to have a quality criterion, a figure of merit, to decide which tracks from the ones we predicted exist, which are correct and which are not. Then there's a process called track fitting, which is relatively standard to smooth these trajectories. And finally, there's a track selection, where we finally decide, okay, these are the tracks that we believe actually correspond to what happened in the experiment, meaning we believe we connected the dots correctly. So now let me describe this stage one by one. And the reason why we want to do a complexity analysis of this algorithm and all of its 5 stages is we want to formally establish how efficient this algorithm is or not, so that we can then investigate if it's optimal and if it can be improved, and in particular, if quantum computation can improve this. And so this is essentially the approach we are suggesting here, which is of course standard, but not so much practiced in the high energy physics community. So I think this is really enriching multidisciplinary collaboration. And so again, I just repeat the tracking problem. I have these dots and I want to connect them. Here it's pretty clear that the connection is this one, but here it's very ambiguous and I need to decide what's fact and fiction. Okay, and so there's a few reasonable assumptions that we will do for our analysis of this algorithm. First, we will say that each picture is generated by n particles. So remember, there's a collision, particles are created, they cross these different layers. Here I'm just representing the cylindrical ones without loss of generality. And so every 25 nanoseconds this happens and the picture is taken. And so this is it. So we have each of these points is in fact in 3D space. And so the first assumption is very reasonable. Each picture is generated by n particles, which corresponds to n tracks. Okay, if we have n particles, we have n tracks. Then the other assumption is that each layer of the tracker registers up to n hits, which is also very reasonable. If we have n particles, then each layer will get n particles crossing itself at that layer, and so we'll have n hits. In fact, there could be, if in some geometric construction, if some construction of the detector, there's some geometric overlap of the detectors, then this assumption will not be true, but we could accommodate that without any problem, okay? But for the case of our analysis, without loss of generality, we have this assumption. And finally, we will assume that for any fixed region, of a layer, the number of hits is proportional to the number of particles. Okay, so I just repeat this slide to remind you that we are looking at this part of the CMS detector, the so-called CMS tracker. And so there's the cylindrical layers represented here. There's the end caps, vertical layers here. And then there's these seeding pixel layers, which also has some horizontal, some cylindrical and end caps in itself. Okay, so these will be the layers the particles will be crossing. So they will be going in all directions. Okay, and so here how we are representing the layers. So of course this should be in 3 dimensions, but without loss of generality, we can just make this 2-dimensional picture. What is important is that we have layers, we have particles crossing these layers, in this case in this direction, and each time a particle crosses a layer, a detector will deposit some energy and we have a hit. Okay, so this is the representation of the process here. And I want to acknowledge my student, Duarte Magan, for preparing these nice slides here. And the 5 stages of the combinatorial track finder algorithm are seed generation. We'll go one by one. Okay, so we'll go by. So we have seed generation, track finding, track cleaning, track fitting, and track selection. And so let's go one by one. Let's start with the seed generation. Okay. So the seed generation is, let me consider that the first 3 layers, I will use them as seeds, meaning I will choose triples of points to be the potential origin of a track. And again, this should be in 3 dimensions and helicoidal tracks, but without loss of generality. Here we represent them with lines. Okay, so we use 3 seeding layers. I think now there's some developments for using 4 seeding layers, but this will not change the complexity analysis. So and so now the question is, of these possible hits that I have here in these 3 layers, which ones do I choose as seeds? So I could choose this triple, for example, here in green, but I could also choose this one, or I could choose this one, but I could also choose this one. Maybe there's a trajectory going that way, or I could choose this one. Maybe there's a trajectory this way. So you see, I have many possible combinations. Okay. And so now let's look at this from the transversal side. So imagine now this green dot is the beam coming towards our direction, and this beam has some radius, r max. Okay, so the beam will have a certain radius. So this light green disk is if we were seeing the beam of protons coming towards us. Okay, and then here I represent the first 3 layers, which are the ones we use for the seed generation. And imagine I have these 2 hits here, these 2 red dots. Okay, so trajectories that go through these 2 hits, they must originate from particles within the beam, and so within the beam radius, so within this light green disk. So I could not have particles coming from here crossing there that would come from this event, right? So at most, the trajectories, they need to be encompassed by this line here and by this line here. And so with this natural geometrical constraint, then a 3rd hit from the same trajectory would have to be in this orange region here. Okay, so with this criterion, we could exclude non-physical seeds. So it doesn't make sense to have a seed that has this hit, and then something here outside that orange region, right? So this already helps us streamline the choice of seed triplets. Still, and because in our assumptions, this region should contain a number order n hits, so a number of hits proportional to n. In the worst case scenario, the number of seeds k that can be proposed or considered is order n cube, right? So in the worst case scenario, we have to consider all possible combinations, even if we have a physical criterion to, in practice, simplify the number of combinations of seeds that we can consider. From the computational complexity perspective, we have something that is bounded by n cube, okay? So this is the complexity of the seeding process. Okay, so next we go for the track finding. So how does the track finding work? Okay, for each set of triplets in the seed that we chose, now I'm going to try and predict what will be the next point in the next layer. Okay, so imagine I chose this seed, these 3 points here in green, and now I make a projection, a prediction, and I will explain how this is done. I make a prediction that the track will go in this direction. And so I don't know yet if the red dot is there. I just make a prediction based on the green dots. Okay, so I make this prediction, but this prediction will come with a certain uncertainty. But at this stage, I haven't looked at layer 4. I'm doing everything based on layers 1, 2, 3. So I predict that the trajectory would go this way with some error. There's some noise, some error, which is this yellow region here. This is my prediction for layer 4, but now I can go to layer 4 and look at this yellow region and see what I have. And what I have is, in fact, I have two hits already there, this one and this one. And so now I can consider them as part of, one of them as part of the track. So my prediction actually hit a region where I had at least one, or in this case, 2 hits. So I'm going to say that the trajectory is this one here, and I have to take into account that maybe it's not this trajectory here, maybe it should be this one. These are within the yellow region of my prediction. So it could be this one, it could be this one. Which one is it? I don't know, we'll have to see. Okay, so these are the 2 possibilities. So now I have a duplicity of possibilities. And now what I do for each of them, I do the same. So now here I'm in layer 4, using the previous information of the previous layers, I make a prediction for layer 5. I'm trying to change my, sorry, just try to change to a laser pointer to be more visible, because the mouse is white and I couldn't see my own mouse. So I make a prediction for this guy, or I consider now another trajectory could be this one, and using this information, I make a prediction for the next layer. Before I look at the layer, this is just a prediction. And these predictions come with some error bars. And now, after this prediction, I go and look at what's the information. I measure the information that is in layer 5. And then I decide, oh, yes, I actually have a hit within my yellow region. So this is probably the trajectory, and so on and so forth. So I continue. So here you see that my prediction reaches a hit point. So that's a good sign. Here my prediction predicts a hit should be there, and there isn't one there. So you know, here it looks good, here it doesn't look good, but you know, maybe there was a flaw in the detector, maybe the particle actually went there, but for some reason the detector didn't record it. So let's assume it could be, and I continue doing this, and then I go next. This trajectory here, I predict, without looking at the new layer, I predict there should be something here in this yellow region. I look at the layer, it's there. Here I do a prediction, it should be, something should be in this yellow region, nothing is there. So this is not looking very promising. And so I sort of discard this trajectory. I'm getting too many fake hits, whereas this one looks, it's, you know, the predictions are being met by measurements, by hits that are really there. So this looks like I found the correct track. Okay, so this is the track finding process. Let me now explain a bit more technically how this works so that I can do the computational analysis. So essentially, this is a well-known process called the Kalman filter. And so the way we describe the state of the track at a given layer K is by 5 numbers, a vector of dimension 5, which is the three-dimensional coordinates of the point of origin, and then 2 features of the helix, the radius and the pitch. Yeah, because the angle will be determined by the magnetic field. So the radius, the pitch, and 3 points of coordinates in 3D space. And so this is 5 coordinates. Okay, and so as I said, what we do is given the information of the previous layers, so the layers up to k-1, then the points in layer k, so the vector p at layer k, this is given by the information of the vector in the up to the previous layer, so p k-1, and this has a relation by some operator f of k, which is called the process matrix, which is a linear model in this Kalman filter theory, plus some noise in this process. Okay, and this is my prediction for layer k according to this Kalman filter approach. And then I go to layer k and I measure. I look, do I have hits in that yellow region, yes or no? And so this measurement at layer k is done by, again, a measurement matrix according to some linear model, acting on the prediction I made for that layer plus some error in the measurement. Okay, and so the Kalman filter, so I'm just trying now to put the bit more technical details in this illustration that I gave before. And so there's 3 stages of the prediction, and then the filtering based on the measurements and the smoothing of this information. So the prediction, as I said, so given measurements up to layer k-1, we can predict the state vector at that layer, and then based on this we can actually predict the position or the vector in the following layer based on the information before, and that's what I've described in the animation, let's say, related by this process matrix. Okay, and so that's the prediction, and then we make a measurement and we update the prediction. So p of k given the information up to k, meaning all the prediction we did with the previous points plus the measurement looking at the hits that are in the same layer, and so this is what we had before, plus some gain that is described by the Kalman gain matrix. Okay, and so what we have is now we look at chi-square, the statistical measure, as a figure of merit for the quality of these predictions. And maybe in the interest of time, well, anyway, so I can go into these details. So essentially, the chi-square at layer k is the chi-square from the previous layer plus some residues that come from the moving to the next layer. And so the point here is that this chi-square is a figure of merit, and the lower the chi-square for a given computation of these different options. So remember the drawings I showed you before, we had a possible trajectory this way and then a possible trajectory that way, but this one was not hitting so well, and so this chi-square, this uncertainty, let's say, would be too large. And so we can, we chose the process or the predictions and with the lower chi-square, and this will be a better fit corresponding with the measurements we compare. Okay. And so when we have multiple compatible measurements, which was the example I showed you, right? So when we go from layer 3 to layer 4, there were 2 possibilities. I mean, I predicted things would be in the yellow region here, and it turns out that then I look at the yellow region and I have two hits that could be possible solutions. And so what we want to do is we want to bound this multiplicity, okay? And so we only keep up to a constant number of tracks from step to step, typically 5, okay? So we do not allow for more than 5 options, okay? Because imagine I have, 100 points here, then I would have to consider a multiplicity of 100 trajectories from layer 4 onwards, right? So the multiplicity would be huge. And so this is not reasonable. I'm sure there aren't 100 trajectories possible from this point. So we have to have some relatively arbitrary but reasonable criterion. And so this, what is used in this algorithm, which was not developed by us, is 5. Okay, typical. Okay, and so at most we consider a multiplicity of 5, and anything that doesn't fit the figure of merit and is beyond that, we discard. And this is very important because this means the multiplicity is kept constant. And this is key for the scalability or the scaling analysis of this part of the algorithm. Okay, so at each layer we perform filtering for order n candidate measurements. Since we propagate only typically 5 tracks, it doesn't matter if it's 5, it's a fixed number, it doesn't depend on n. And so the seed develops into a constant number of tracks. And so if k is the number of tracks found, we have that k scales like n cubed. Okay, coming from the seeds that we have, the n cubed seeds that we have. And so this part of the track finding is the following. The track finding has complexity, the number of seeds we have, time the n tracks that come, let me go back, that come from here, right? Because we're considering n tracks. And so since k seed is n cubed, then the track finding component will be n to the power 4. Okay, and this is it. Okay, now we go to track cleaning. And so you see that the green trajectory. So we did the track finding, and now we have these solutions. Blue seems good. There isn't much ambiguity. Purple at the beginning, there is a bit ambiguity between purple and orange, but then here it looks good. The orange here, it has ambiguity with purple. There's ambiguity here with yellow. This pink here, there's ambiguity with yellow, and then ambiguity with green. Green was looking okay, but then there's ambiguity with green. So with pink. So this is what the track finding gave us, but it's still not so clear which of these are real tracks and which of these are a wrong hypothesis. So we go for track cleaning. And track cleaning, you want to eliminate these. Okay, so for example, track cleaning, just as an illustration, would find out that the pink one was wrong, and so what we have is the yellow and the green, and so on. And so what's the criterion to eliminate this pink one here, as opposed to eliminating the green or the yellow? Okay, so the track cleaning, the way it works is to avoid having multiple tracks describing the same particle. We do this criterion for cleaning. So we calculate the fraction of shared hits between all pairs of track candidates, right? So if I go here, you see these points that have these hits that have 2 colors, they are being shared by 2 candidate trajectories. So, and the criterion is, I calculate the fraction of shared hits between all pairs of track candidates. So I consider all possible pairs, and I divided the number of hits shared by the minimum number of hits for each of the tracks in that pair. Okay, and if for any pair this fraction exceeds a fixed threshold value, typically 20%, then the worst of the 2 tracks gets discarded. Okay, so we have this criterion to clean the track. And so at this stage has complexity k squared, because we are comparing k tracks pairwise, and we have k equals to n cubed, still coming from the seeding stage, and so if k is order n cubed and this is complexity k squared because of the pairing, then the cleaning stage has a complexity bounded by n to the power 6, which is very dominant. If you see the previous processes was n cubed and 4th, so it seems like cleaning, which is a pretty simple process, is really costing us heavily for the complexity. So can we do better? And so we actually thought a bit about this, and so this is the solution that was developed. And this is all classical, and then I should accelerate to the quantum part. So let us what do we want to do? We want to ensure that there are no two tracks sharing a given number of R hits. Okay, otherwise this is too ambiguous. So we want to find those that don't share that many hits, so that we can then decide which of the tracks in that pair we should keep and which ones we should discard. Okay. So suppose, for simplicity and without loss of generality, that all tracks have the same number of hits m. Okay, so track 1 will be composed by the hit in track 1, hit 1, hit 2, hit m. Track 2 will have hits h1, h2, hm, and so on until tk, which is the number of tracks. Okay, so now we can consider a combination of R layers. Okay, so for a given combination of R layers, so here let me go back. Here we have all the layers, right? So now we consider a combination of just R layers, and we consider the restriction of the entire track just to R layers. Okay, so instead of going up to M, we now stop at R. So it's the same that we had before. And now what we can do is just a lexicographical sorting of these tuples of dimension R. Okay, so we just have some lexicographic criterion, which is quite arbitrary, but we can do it. There's nothing stopping us from doing that. And so we do this sorting according to this, let's say, labeling to simplify it. And then whenever there are ties, we can break the tie with the chi-square figure of merit. Okay, and so now we can go through this sorted list, and whenever we have two tuples that are the same, we select the previous one to get rid of this multiplicity according to that quality factor. And so what happens here is, so this arbitrary selection of R layers is M choose R, so it's a constant number in terms of complexity. We have K tracks, so the choice is order K. And then this lexicographic sorting is order of K log K. This, I won't go into the details here, but this is something that is not hard to see. And then the sorting, which in fact could be embedded there to some extent, is order K. So in the end, we have a constant plus order K, K multiplied by log K and K. So what is dominant is this factor here. And so in the end, we show that the complexity of track cleaning with our proposal is K log K. And this is improved with respect to the naive K squared. And so if we now plug in to, and so remember that because then we have K cubed. So here, instead of K to the 6, we would have K cubed log K cubed. So, so this is a significant improvement, classical, just based on our analysis. So this is already an advantage from our analysis of a classical algorithm. We still haven't done anything quantum, and we're already finding a way to improve this selection process. Okay, let me speed up a bit now. We have some track fitting, which is some sort of smoothing, typical smoothing of curves with the data points we have. So just illustrated here, because this is quite standard. And so this is the track fitting. This is used the Kalman filtering, and so this depends on the number of clean tracks. So this will not change the complexity. It's whatever number of clean tracks that we have. It doesn't change the number of clean tracks. Okay, and then finally we have the track selection. So see that here we kept this orange trajectory even after the cleaning and the fitting, and so we have to have a selection criteria, and in the end we're going to get rid of this one. So I put it here in gray to say disappear. Let me go back. I still have not eliminated this one. I had eliminated others. This looks good, this looks good, this looks good, this one looks good, but this one is still a bit ambiguous, so I have to select. So how do I do track selections? There are some fake tracks there, and so we just use a selection that will not change the number of tracks. We need to look at all of them. We just have some fixed quality criteria, some figure of merit, similar to the ones described before, but from the complexity, this doesn't matter, this doesn't change the complexity, the number of tracks will not change. So in summary, the complexity of the algorithm with its 5 stages was dominated by the track cleaning, which was n to the power 6, and we were able to reduce this to n cubed log n. So this, we already have an improvement on this classical algorithm. Okay, let me now move to what should be the key part, but to get to this key part, it was crucial to explain this classical problem. Can we improve tracking with quantum computation? And this is not obvious at all. And this is an interesting lesson in itself. And okay, so many stages of the tracking problem can be formulated as search problems. And so one question that could emerge is, can quantum search be used for speeding up tracking? Okay, so let me briefly tell you about quantum search. So imagine you have this labyrinth or pseudo-labyrinth, and you're the Greek hero Theseus trying to find the Minotaur in this labyrinth. And so you just have to go around until you get in this graph, until you get the right vertex. And could the quantum approach help? And in fact, yes, you get a quadratic speed up, because quantumly you could travel in superposition of different paths, and this will give you a speed up, which in fact one can prove is the optimal speed up afforded by quantum computation. And so could we explore it here, right? This looks promising. Well, we did that. It's not that simple, but for most parts, this will not improve the complexity. So quantum computation doesn't always improve, doesn't always offer a quantum speedup, right? So here's a quick example. So so let's see what we can do. So let's look at sampling, seeding. Okay, so not every triplet is a good seed, right? So some triplets will be indeed the 3 first points of a trajectory. Some triplets will not be a good seed. So instead of checking the triplets one by one, we could use the quantum search to sample good seeds. Okay, so imagine I have some quantum circuit with an oracle that, given 3 hits, tells me if this is a good seed or a bad seed. Okay. So using Grover's algorithm, which offers a quadratic speedup, we could sample all k seeds at the same time, and so we know that this is we have a search space of dimension n cubed, and so the Grover solutions with the Grover complexity, the complexity of the Grover's algorithm for finding something in a search space with multiple solutions will be given by square root of, in this case, n cubed divided by the number of solutions that we're looking for, k seed, and we have to do this for every seed, and so this will in the end be order of square root of k seed times n cubed, but because k seed is of the order n cubed, this doesn't change. In the end, we have n cubed as we had classical. Okay, so in the worst case scenario, this is not better than this quantum search approach is not better than the classical performance. Okay, so where can we find quantum speedups? Well, so quantum search only provides advantage if we have some guarantees on the number of solutions. So now we have to look which tasks in which tasks is the size of the input much larger than the size of the output. Okay, and so this is the combinatorial part of the combinatorial Kalman filtering in the track finding stage. So this is what we're looking at. So remember, now I rotated my picture, so I have the 3 layers of the seed. With this, I predict layer 4, and now I'm trying to predict layer 5. Okay, and I have all these possible hits here. So at each layer, we perform filtering for n hits. But as I said, we had this criterion, or the current used approach has this criterion that we only accept a multiplicity of, say, 5 or so. So the multiplicity is kept constant. There's no propagation. So so we can use a quantum search algorithm to decide which hits to keep here in this choice. right? So we propose this quantum filtering. So we assume we have quantum access to some filtering routine. This means that there is a quantum circuit U filter controlled by the current state that allows us to compute the filter chi-square value for a superposition of hits. Okay, so say I have a superposition of hits here, and this is able to, given the information about the previous layers, make a prediction and the corresponding figure of merit in terms of the quality factor chi-square based on this. So I could compute things in quantum superposition. This unitary, it runs in constant time because it doesn't depend on the total number of tracks, right? And so if we use quantum search for maximum finding, which is a standard process, we can find the constant number of best hits, in the sense that they have the lowest chi-square criterion in O square root of n quantum time per seed. And so this yields a quantum complexity of the track finding stage of k seed times square root of n. And remember, we have n cubed seeds. And so this means we now have a total complexity of n to the power 3.5, whereas classically in the combinatorial track finder algorithm, we had a complexity of n to the power 4. So quantum computation is offering us a small speed up. This is something we found. It's not much in practice, maybe is not that useful, but it's the best that quantum computation could yield, at least in our analysis. And so I'm about to finish, and I think this coincides also with the time I have. So let me summarize the results. So this combinatorial track finder algorithm has these 5 stages: seed generation, track finding, track cleaning, track fitting, and track selection, which I analyzed, described to you one by one, and then did the classical computational analysis of each of them. And what we found is that the track cleaning, we could actually, our analysis inspired us to improve the complexity there. So instead of n to the cube, which was the dominant factor in the overall complexity analysis, we could reduce it to n cubed log n. So this is actually, the classical improvement is actually our best improvement. And then we showed that the quantum approach couldn't really improve much. It couldn't improve the other stages. It could only improve the track finding. At least that's what we found. Okay, and so I go for my conclusions. So what did we do? We have analyzed the computational complexity of the combinatorial track finder algorithm, which is the state-of-the-art method to do particle tracking at CERN, at CMS. Okay, and by doing this analysis, what we found, a way to improve, we have a classical improvement on the classical state-of-the-art algorithm, namely for the track cleaning stage. And we also found that the quantum approach could not improve most of these stages, but we could improve the complexity of the track finding stage. We couldn't improve much, but we could actually improve. So what's the lesson here, and what did we achieve? Well, this was, to the best of our knowledge, the first example of a complexity analysis to investigate and benchmark future quantum algorithms in high energy physics problems. Because now there's this real strong excitement, which I'm also part of, and which I'm also promoting, namely with this project that I'm coordinating, Quantum Computation Solutions for High Energy Physics. And also, in fact, we created a seminar, the QUANTEP seminar, Quantum Computation and High Energy Physics seminar, that we've launched online last October. It's been very successful. We've had many people attending our seminar. So if you're interested, let me know, or just Google QUANTEP seminar. And we have all the lectures are on YouTube. We have a seminar once a month, typically the first Wednesday of each month, 5 p.m. Central European time. Okay, and so there's lots of excitement about what's the potential for quantum computation in high energy physics. And you see, CERN just launched their own program on quantum technologies last January, just a few months ago. Fermilab in the USA also launched last year a program in quantum computation and quantum technologies. So this is a really exciting frontier to explore and understand to which extent quantum information science, quantum computation can help address these very hard computational problems that particle physics generates. And I would argue they have the hardest computational problems on Earth. And so there's a lot of work that is now starting. And so this is very interesting because this is truly multidisciplinary and the two communities need to learn from each other. And in terms of this tracking and jet clustering algorithms, we also work on that. I didn't mention, I should have mentioned, we have a quantum annealing algorithm for jet clustering, which is a sort of variant of tracking. But otherwise, most of the approaches are based on quantizations or quantum versions of the classical machine learning approach. And so typically, let's say quantum machine learning approach, so the global methods. And here we, I think, do the first attempt with a local method, a bottom-up track-by-track reconstruction. But most importantly, I would say, to the best of our knowledge, this is the first full complexity analysis of these problems and of these classical solutions. And I think this is the message we want to convey. We need to understand exactly what the classical complexity is so that we can benchmark future quantum algorithms and understand if they're advantageous or not, right? Again, I understand that for high energy physicists who are really working with data, they don't care about asymptotic limits and worst case scenario scaling with n cube. They want concrete numbers, and they are right, of course, and that's what they need. But if we are going to ever understand if quantum computation can offer an advantage or not, then we need to do this proper and in-depth analysis and investigate what quantum computation can offer or not, and benchmark these solutions to understand how much advantageous quantum computation is or not. And this, I think, is essentially the message here. And I think this can be very profitable, because what we found in this particular problem of tracking is that quantum computation maybe cannot help that much. But by doing this analysis, we actually found a way to a classical improvement on the classical algorithm that may be more interesting. And so this is just a first step and the first example of what we believe this research agenda should consider. And we will have very soon, I think before the end of this month, we will have an archive with all the technical details on this work. So thank you very much for your attention. Let me thank my group and the collaborators in this very nice work, and repeat my conclusions and be at your disposal for questions. Thank you very much once again. I hope I went okay with time.
Yes, so thank you so much. It was really an interesting talk that opens potential new applications for quantum computing. And I'm sure in future there will be further improvements to what is available classically. I would like to ask now Professor Murad Telmini from the University of Tunis El Manar to guide us through the questions. And Murad, if you would like to give a look at the Q&A and maybe pose the questions to Yasser, we still have a little bit of time to address a few questions. Thank you.
Yes, thank you very much, Francesco. Thank you, Yasser, for this beautiful talk. You took us to this journey in the complex physics of high energy collisions and how to find the good algorithms to minimize the cost of the calculations, to optimize the resources. Thank you so much. So indeed, we have a few questions here in the Q&A box. Some of them are a bit general, some others are specific to some points related to some slides. So I hope we will be able to track them back and so that you can address them. Before the announcement of the Q&A box, we had also some questions in the chat part of the Zoom meeting. May I start with one general question asked by Sean Weinberg? How is CERN and other facilities making use of ML models in detection phase? And Sean says clearly that this question is not directly related to the topic of the talk itself.
Sure. So,
Yeah.
so the use of machine learning. I don't know exactly what you mean by detection phase, but if it's in this context, I would say that so CERN since the 80s, I think, has been working on neural models, neural network models. So before we call this machine learning, and in fact, one of our collaborators, Ron Seixas, who is also now in my group, he's a high energy physicist. He was one of the people in the 80s or 90s pioneering the use of machine learning or neural networks, as it was called at the time, to try and select data, right? So because, this continues today. Like boosted decision trees, etc. So this is a very powerful machinery. Machine learning, neural networks is a very powerful machinery that is used very, very significantly in the analysis of data in particle physics experiments.
Okay, thank you, Yasser. The other questions are more related to the talk itself. So I think the attendees who ask these questions are particle physicists. For instance, here we have some questions related to the algorithm, to the combinatory track finder algorithm, probably around the slide number 52 to 60. One of the questions by Swagata Malik is, how do you decide which data pictures to discard? And another related one by Malika Amari is, why don't you use all possible triplets?
Okay, thank you very much. So I must say that I'm not a particle physicist, and so I've been learning quite a lot. It's been very interesting discussions and interactions. So I'm not familiar with all the details of how these things work, for example, at CERN. Okay, so there's some quick, what I understand is there's some quick decisions at the trigger level where they try to understand what is physical or not, what hits correspond to something that is physical or not. And so there's a bunch of criteria that I don't know the details of to do this quick selection and discarding. But in fact, this is all based on, semi-arbitrary criteria based on the physics we know and the technology of the detectors, and so what we can guess, what we can estimate, but we cannot exclude that we may be losing very precious events in the data we discarded. So it's just quality criteria based on reasonable assumptions given physics and the technologies. So for the choice of all triplets, in fact, you don't need to in practice. So in our complexity analysis, it may be such the experiment may be such that all triplets are within what is physically acceptable. But as I tried to show in one of these pictures, let me go back to this picture. Oops, I think I went too fast. Okay, this here. Okay, so this again, this green disk is the beam where the protons are. But the bunch of protons is coming towards us. Okay, so we see a transversal cut, and there's a certain maximum radius. This is confined, right? And so we know that all protons in that bunch must be confined in this green region. And so you cannot have trajectories originating from outside this region. So for example, for these two, at most, the particle should have emerged from somewhere within this disk. So it cannot have emerged from here, and the trajectory could not go, for example, this way, right? So just by our knowledge of physics and geometry, we know that the third hit for this triplet would have to be in that region. This is just a very simplified diagram. And so if in practice, when we do the actual data analysis, then we should definitely use this knowledge, this precious knowledge, because then it reduces our work, right? But for the complexity analysis, I have to consider the worst case the worst case scenario, and it may turn out that for some strange reason, all possible combinations would be physically allowed, and that's why the complexity is order n cubed. But in practice, just because of physics and geometry, we can exclude a lot of things. So in those cases, for the practical calculations, we should do.
Okay, thank you, Yasser. We have also some questions in the Q&A box. Several questions from Naleli Machello. So probably I will pick up one of these questions and kindly invite Naleli to probably contact you for details, because these are very specific questions. I think Naleli is a specialist of this detection and trajectories physics. Well, so one of the questions is, shouldn't all possible starting combination be considered and let the estimation process assign the likelihoods/weights of one starting combination relative to others?
Oops, I was muted, sorry. This is certainly a possibility. Again, I'm not an expert on this. I'm not an experimental physicist and in high energy physics. And so what we found, actually, just a curiosity, even talking to our colleagues and collaborators in my group who have the experimental particle physics background and work at CERN, collaborate at CERN, they themselves were not so familiar with these algorithms. So in fact, it turned out that only a few people actually are familiar of how these algorithms work, and it's not that easy to find the methods that are being used now. They are not always public and not published. But I'm not addressing the question directly. Let's now address the question, but I wanted to give this context. So I don't know that much, and so there could be other better approaches. What you suggest is certainly reasonable. So what we did is we looked at what, to the best of our knowledge, is the state of the art used at CERN, in particular at CMS, and that's what we took as our analysis. Other labs or other experiments may use variants, but our understanding is that even if the other methods are not exactly the combinatorial track finder algorithm, they cannot diverge too much. But having said that, we are always open to analyze other approaches. This could be very interesting, and we don't know much about variants. So we'd be very interested in learning and considering other classical approaches that we could analyze and try to compare with quantum solutions. So this is really a multidisciplinary effort, and your expertise on the side of high energy physics is extremely precious, and of course we would be very happy to dialogue in more detail at the technical level about it.
Okay, thank you, Yasser. We have a couple of questions related to the second part of your talk, the quantum computing part. So it's really exciting to see how quantum computing can be applied at this large scale, from high energy physics, huge facilities like CERN accelerators, to tabletop physics. So we have a question from Camille Lombard-Latune. I take this opportunity to say hi to Camille, if you don't mind. So the question is, if I understood well, the first attempt to quantum improvement does not work out because k-seed scale as n to the cube. What if we had k-seed scaling as n to the fourth, as it might be in the future if the seed layers become to be 4?
Okay, thank you very much. Indeed, thanks for that question, Camille. Indeed, we are based on triplets for seeds, but we are aware that now there are approaches considering a fourth point. And as you can see here, I mean, our analysis is for whatever number of seeds or behavior of the number of seeds we have, right? So if we choose 4 seeds, then this would become n to the fourth. And that's why we wrote here everything as a function of k seed, because k seed can be, as you said, n to the fourth. So then you would just, where you have cube, you just put fourth, and you change these equations. But you would also change the classical ones, right? So I think then the speed up, the essential aspect of the speed ups hold. So we were careful to represent things all as a function of k seed, and to say here, you see, we put for k seed in general. K seed could be n cube, as we do, or it could be n fourth, as it's now being considered for present and future. So we are ready for, I mean, our analysis takes that into account.
Okay, thank you. We have a last question in the QA box from an anonymous attendee. He will recognize himself, certainly. So the question is about the oracle. How can you elaborate, the question is, can you elaborate on how the oracle looks internally in your track finding quantum algorithm? In short, how did you construct it for your simulation studies, for example?
Okay, so first, we did not do any simulations. And so we did not construct this oracle. And so this is a very good question, because then we would actually have, so we are just, we can make this assumption that it's possible to construct such an oracle, such a circuit, okay, and we can do it. And so with then so I'm not entering those details here, but in our article, then this will be described in more detail and show how this can be done. But so just to answer here is that I can just look at this filtering process as a unitary process, a unitary operator on those vectors, and so convert those Kalman filtering matrices, or adjust them to, I just need them to satisfy unitarity, and that's it. So we essentially are based on the classical filtering, and then we have to have a criterion regarding the chi-square figure of merit. And so we need to just explicitly encode that criterion in the circuit. Okay, but this is not that challenging. This is doable.
Thank you very much. These are all the questions we have here. Thank you once again. The floor is yours, Francesco.
Yeah, Murat, thank you very much for guiding us through the Q&A session. And it is probably now my duty to thank Yasser once more for his time and for the excellent talk. And I'm sure that in the near future we will invite you again to give us an update on how quantum computers eventually beat the classical algorithms for application in high energy physics, because eventually I'm sure we will manage. Yeah. So thank you very much, Yasser. And I would like to thank also our participants for joining us this afternoon, and remind them again that in just under 2 hours, we have another exciting talk on the program to celebrate the World Quantum Day. So you just have time for a cup of tea, and then you're back in Zoom or in YouTube. Yeah? So we are looking forward to that as well. And I would just like to ask if our panelists are happy to switch on quickly their video, so that we can take a photo of the group of panelists. I will not ask the participants to do the same, because otherwise, if we need the logistic of switching them to panelists would probably take too long. But Yasser, if you could stop sharing your screen, then we have the opportunity to see everybody a little bit
Yes.
in the gallery format.
Excellent.
And I will ask also Ilya to take the screenshot as well, just in case I fail miserably, which is a possibility. So a big, there is still, Rania, please, can you switch on your video?
And Mahamiza?
Yes.
Makamiza as well. Sorry, I missed Makamiza. Okay, fantastic. Let's wait a second for Makamiza. No, Makamiza is on. Sorry, Makamiza is
you have two connections.
Another gadget for the
you have two connections, sorry.
Audio also. So a big smile, and let's take one more just in case it doesn't work. Big smile, thank you. Voila, perfect. I will share the photo with you afterwards. Yeah. So
Excellent.
Thank you very much again.
Thank you very much.
Yasser, for your time, and thank you for all the colleagues across the African continent. And I really hope that, no, I don't hope, we will just do it, that maybe in the next week or so, maybe we can organize a meeting among us to see how we can organize similar events on a regular basis so that everybody can participate and we can promote a little bit more of quantum in our part of the world.
Yeah, I mean, I think that's great. So thank you so much, Francesco, once again for the invitation and for the organization. Thank you all for participating, and it's nice to see some of you who we haven't seen in video before, like Usama and Girish and Rania. Some others you participated in our first network meeting, so we had the chance to meet there. So indeed, I think it's very important to develop these things in Africa. And I think we should use the World Quantum Day Network for that as well. So the key goal, as you know, it's outreach, and outreach to the general population, but it can also be to stakeholders, to political deciders who may want to decide investing in this area, etc. So the World Quantum Day is for us to do whatever we believe it's nice and interesting with it, and that should definitely include cooperation between scientists and between countries and continents and programs. So count on me. I'm very passionate about that. So I would be very happy to see this develop also that way. So let's then have this meeting. I would be very happy to participate as well, so that we can think not only what could be done in Africa. This is up to you guys. You're representing Africa, but also how to connect it to, for example, what we do in Europe or a global initiative. So I think this would be very nice.
Thank you very much, Yasser. We will definitely come back to you very soon. So then, thank you very much, everyone, and I hope you all again at 5 in the
yes, 5 Central European time, 4 p.m. Western European. So is there a chance to save the chat with the questions, or?
Yes. I will. I think Zoom saves it automatically. I will be very happy to email it to you afterwards.
Okay, excellent.
As
Thank you very much.
The recording is done. Yeah, perfect. Thank you.
Thank you very much, Francesco. Thank you, everybody. Happy World Quantum Day, and see you soon.
Thank you.
Bye-bye.
Bye-bye. Thank you. Bye-bye.
Thank you very much. Bye-bye.
Bye. Thank you.
Bye. Thank you.
Bye, Michael. Bye-bye.